Can everyone hear me in the background? Cool. Welcome to Space Drafts 87. Thank you so much for joining us. We are part of an international network called Astronomy on Tap, which is basically just public astronomy talks taking part in bars across the world. So thank you for joining us here at ours. My name is Lily Whitler. I am a PhD student at Stewart Observatory, and this is the only other co-organizer who's with me here in town, Tim, and a whole bunch of contingent of graduate students here. So I'm going to put them all on the spot and say, if you ever want to come talk to us about space, please do so. Tonight we have two amazing speakers lined up. Eden McEwen from Optical Sciences Department, graduate student, and also the very recently minted Dr. Harry Krantz from Stewart Observatory. He got his PhD like a couple weeks ago, so please give him a hand. So just a few housekeeping items before we get started. We have merch over here, so feel free to come visit us at any point during intermission after the show. Please buy our merch, please give us donations, please come chat with us, we'll be happy to do all of that. Tip your bartenders. Oh, and I do not have a drink with me, but as many of you who are Space Drafts regulars know, and as you may have heard earlier, we are right next to an active train track. So if the train comes by and it makes it so you cannot hear the speakers, we like to raise our glasses, toast the train, and say, what? Choo-choo! Hopefully that will not happen too many times tonight. Last month it happened like 3 times during one talk. So cross your fingers that will not happen again tonight. So without further ado, I'm going to welcome Eden McEwen to the stage to tell us all about life as an observational astronomer.
Thank you, Lily. Can everyone hear me okay? Hi, my name is Eden McEwen. I'm a first-year graduate student in the College of Optical Sciences here at the University of Arizona. I'm going to tell you about all the telescopes I've loved before. So I call myself an observational astronomer. I go to telescopes, I look at stars, but I didn't have a typical astronomy backstory, and I'm here to kind of walk you through how I got to where I was, because I think observational astronomy isn't something that is very easily accessible to the regular public, and that's what these talks are for, is to kind of bring you into our lives as astronomers. Alright, so if you ever apply to astronomy PhD programs, you'll usually get the advice: the admissions committee does not care that you got interested in physics and astronomy by looking up at the stars when you were young. Leave the cliches out. Basically, everybody has this moment when they're young, when they're looking at the stars and they're like, oh, we live in this place that is so small among something so large. And no one on an admissions committee wants to hear that from you because they want to hear why you're different from everybody else. However, I didn't get into astronomy that way, and I love cliches, so I'm going to go exactly against this advice as I walk you through my story. Just to say I taught you some science and go through some basics, I'm going to answer the question, what is a telescope first, so we're all on the same page. So how do we see a star? So a star is something very, very far away. It's a hot ball of gas, burning, and emitting light. And that light, as it gets to us, we focus it down to the back of our eye with a lens in our eye. And when you're looking at the star, your pupil is usually very large, and that's because you're trying to get in as much light as you possibly can. So when you're looking at a star, the diameter of your eye is usually around 10 millimeters, or half an inch. But you can imagine when things are very bright, you close your eye because the receptor cells in the back of your eye don't want all that light. And so you shrink the diameter of your eye so that you don't get overwhelmed. And the point I'm trying to drive home here is that the diameter of this lens, or this collecting circle that you have, influences how much light you get. And for stars, we usually want to get as much light as we can. And so I'm going to talk to you about telescopes, so I'm going to talk to you about their different diameters, or the size of the telescope, because it impacts what kind of science we can do based on how much light we get. So a refracting telescope, or telescope with a lens, you have lenses in your glasses and things like that, works by enlarging an object very far away. It also collects more light. Light from the star comes, travels a very, very long way, hits this lens of a refracting telescope, and focuses it down to the size that your eyes can see while collecting more light. This does two things. It means you have more light to work with, and it also means you can resolve two things that might be close. So if you have two stars orbiting each other, the more light you collect and the bigger your telescope, the more likely you are to resolve them or see them as different. The diameter of a lens telescope The diameter of a lens telescope is usually on the order of 80 millimeters diameters are 4 inches. There's optical reasons why we don't really want to get bigger than that, and some of them are aberration dependent. Hey, Amtrak. So some of them are aberration dependent. So I keep thinking he's done. You know, if we had faster trains, this would go faster. Improve our public transit. Sorry. Okay, where were we? Okay, yeah. So this big thing of glass is actually a limiting factor in refracting telescopes. So we can only make a piece of glass this big, so accurate, and it weighs itself down. So I'll start by talking about older telescopes that do have refracting lenses, but eventually we're going to get to the point where we can't get bigger, so we need to change the type of telescope. But I'll leave that as a teaser for later. Alright, so here are the start of my love notes. I am going to start, ooh, they did not have my font. That is okay. Imagine this is scrawly and very homey. Okay, we're going to start with Griffith Observatory, Los Angeles. We're going to call it my celebrity crush. If you're a public school student in the LAUSD area, you've been to Griffith Observatory. It is the free place to take your 8-year-olds on a field trip. That does not mean I love it any less. I went like 4 times, a big, hot, yellow school bus. It's smack dab in the middle of LA, so that is actually the downtown skyline you're seeing in that photo. It's in Griffith's Park. And it was always meant to be an educational telescope. It's built in the middle of a big city. They knew they were going to have light pollution. They knew they were going to have pollution in general. But they built it kind of as an idea of being one of these places where we could go as a monument to science. So it was built in 1935. Griffith Observatory is only at an elevation of 1,000 feet. I say that now so you can be impressed by the elevation of later telescopes. It's a 12-inch refractor, and this is what it looked like kind of back in the day. And they claim they're the most look-through telescope in the world. And that's because they're very easy to get to, and a lot of telescopes are not easy to get to. So if you look at this diagram of when it was being built, you can see this back dome, that's a planetarium, and these 2 side domes are actually what can be counted as telescopes. And then inside is actually just science. It's the Science Museum. Great for your 8-year-olds. And so you can see it as kind of like a tourist destination of the world. It's one of those places Apple Maps makes like a little 3D model because they love it so much. Here's that same 12-inch refractor over here. On the other side, I think they have a solar telescope. You can see the LA skyline over here, and then just a big monument to a bunch of male astroscientists and physicists and such. And over there's the Hollywood sign. All right. So we're going to say that this is my celebrity crush. She's not functional, but she's pretty. I never really got a functional working relationship with her, but it was one of those things where I was like, that's cool. We do that. We build things like that. I'm interested. All right, now we're going to talk about Lick Observatory in San Jose. We're going to call this my childhood sweetheart academically. Because Lick Observatory is actually in San Jose, California. I went to school in the Bay Area, and so this is something I heard about from all of my friends. It's down here, so it's kind of between, I went to Berkeley, so Berkeley is up here, and then Santa Cruz, Santa Cruz is down here, and the UC system, so the University of California system, kind of has shared ownership over the Lick Observatories. UC Observatories is what runs them. And it is home to the 91 centimeter or 36-inch refractor, built in 1888 at an elevation of 4,200 feet, and it's the first permanently occupied mountain observatory, and this was big. Not only that, it was the largest refracting telescope until Yerkes in 1896, and I'm not going to get into it, but Yerkes wasn't used for very long because they built it inland. The cool thing about Lick is it's actually close to the coast, and so you get usually a pretty good airflow going from the ocean breezes, which is one of the things that Yerkes didn't have. And the story, so this is a very beautiful image of that dome, but the way they got the money for this telescope is a bunch of astronomers in the 1800s were very good at convincing rich people that they should be building telescopes, which is a skill that we need to continue, everybody, all the astronomers in this audience. So Lick was a wealthy man man who came to San Francisco, like a lot of people were in that time, and he was determined to build a monument to himself. He was a great businessman, and was destined to be remembered forever. And his first idea for doing that was a giant pyramid in the middle of San Francisco. And then an astronomer said, I can give you one better. How about an astronomy temple? And so they built this on his money. They promised him they were building one of the biggest telescopes in the world at that time. And he ended up being buried here. So you can actually go see Lick's grave out at Lick Observatory. And it's currently being used for science. So I was never involved with any projects at Lick, but a lot of my peers were. There was transient tracking, there's a history of discovering moons here. Laser guide stars were developed here, so that's that yellow beam you see. This is the original dome, and here, I can't remember which one this is, but this is a more recent build. And so still like a very active and popular telescope site. And especially if you're talking about grad students developing technology like I would do, this is a really important site because it's good. There's infrastructure here, and you can do small projects. And as I was hearing about these projects, I was like, oh, you can do that as a career? Like, you can do research here? You are allowed to muck around on a telescope still? These aren't just backyard things? So we're now thinking, oh, this is something I could do. Like, this isn't just some pretty place for science. This is a pretty place for modern science. My peers are here. I keep hearing about these things. What are they? And I'm going to talk to you about reflecting telescopes, because that's the next kind of telescope. So previously, remember, we were just talking about lens telescopes. These are mirror telescopes reflecting. So the light from your star comes from very far away, and then the first thing that collects it is actually this back mirror. This is called the primary mirror. And this is one configuration, but you actually have different configurations it can focus to. But let's say you don't care about that, and this is very simple. So we're reflecting off this back mirror. We hit the secondary mirror, which is actually in the way of the beam. Don't worry about that, that's fine too. And then you go through a central hole in the primary mirror. That's also fine. And the thing that really sets reflecting mirrors apart from refracting mirrors is you can build them really, really big. And so we're talking on the order of, remember before we were like 100 centimeters? Now we're up to 3 to 10 meters. So we are big. We're talking like almost tennis courts. These are big science numbers. And if you really want that in inches, that's 110 to 390 inches. This means nothing to me, but if you really want imperial, that's what it is. Okay, and then I just want to tell you a caveat is we keep increasing the diameter, and I tell you this will do more science for you. But there's a caveat, because what do stars do in the sky? They twinkle. Thank you, Ken. So if you look up, you say, twinkle, twinkle, little star. The reason it does that is because we have pockets of hot and cold air between us and the sky. So if you've heard about James Webb, that space telescope, they don't have this problem. They have the straight, they have those straight lines, and they don't have to worry about it because they don't, well, they have some things, but not as bad as we do on Earth. We have all these pockets of atmosphere, and it spaghettifies so our star is twinkling, it's moving, it's getting dimmer, it's getting brighter. Think trying to look at the sun from the bottom of a pool. It's dancing around, and it's playing off of all these other things. It's not as bright as it would be. That's kind of what's happening to our stars. So don't just go and say, like, the bigger diameter, it's going to get better. We actually have to do a bunch of really impressive technology to get rid of that twinkling. That's what I do. But I did not come here to tell you about my research. I came to tell you about telescopes. I'm actually not going to talk about that, but I do want you to know it because that's what pays me. Okay. Moving on, we're going to talk about Palomar Observatory. And this one is my first night. So this is actually the first time I ever got to spend a night at a telescope. I had no business being there. It was definitely not my project. I made friends with a postdoc and she took pity on me. And I loved it. Okay, so Palomar Observatory is in San Diego, California. It's actually, there's a series of telescopes, so I'm not being very clear with what's a telescope and what's an observatory, but Palomar Observatory is the general collection of telescopes on this mountain. Once you have one, it's kind of easy to add more. So I'm talking mainly about the Hale 200-inch, which is this huge dome right here. Palomar Observatory is between LA and San Diego, so up here you have Anaheim, Disneyland, etc. You drive a very long way and very desolate roads filled with, honestly, mostly casinos. Then you get to Palomar, and then if you kept driving, you'd go to San Diego. So we're right in the middle right there. And yes, we're talking about California telescopes because I am from California. All right, so Palomar Observatory The Hale 5.1 meter, 200-inch reflector was a Rockefeller Foundation grant money little nuggets. It's a huge telescope, so this little door here, that's where a person would go through, and this is the dome. This is a huge telescope. The site was founded and they got money around 1928, but the first light was in 1949. They developed new kinds of glass for this telescope, so the mirror back of the way that a telescope mirror works is you get a glass back, you try to make it really light, and then you aluminum coat the front. So it's still metal on the top, but the bottom is glass, and we discovered Pyrex, and we were like, this is great. So we used that for the back of our mirror. And actually, the first astronomer to use this telescope was Hubble. Hubble of the Hubble telescope, of the expanding universe. He was like, yeah, I want to be doing science on this really big instrument. So first light, so it's a 5.1 meter, first light in 1949. And there's one Soviet telescope that was built in like the 1970s after this one, but really, this is our biggest reflecting telescope until Keck in the 90s. So Palomar was on top for a really long time, from 1950s to the 90s. All right, so here you can see a guy sitting in that back structure Pyrex. He's very small. This is a very big mirror. And these are the crew that brought it over, I think, from New York. And then this is what's holding the telescope. There's this big counterweight. This is the tube-like chamber, and we collect light from an open dome, comes down here, and first scale, that's a person. They're right there, that little guy. So this is a big, big dome. So originally, we had in that upper cage, that's where people would be taking their data. So we didn't start having telescopes with cameras, we actually had to take photographic plates up there. And so you have a little operator sitting, collecting data throughout the night. And so we have a picture of Hubble doing that very same thing. So, hello Hubble, just riding in the fun house ride that is our telescope. All right, so now we're gonna talk about my experience at Palomar. Again, just to impress upon you, this is a beautiful telescope. As my mentor said, who brought me to the mountain, he said, this is one of the last beautiful telescopes, Eden. They started making them ugly. This is when they appreciated design in telescopes. And I found it kind of creepy, because inside there was like very wood and like we are from the 1930s, but it's fine. But anyway, impress upon you, that's a person, that's the door, this is the dome. We're talking very big. All right, so now is probably the part that you haven't all seen. So observational astronomy and living in the observational dorms isn't something that everyone gets to do. And this presentation is actually very similar to one I got my first year of undergrad. My mentor explained, she did a public talk, I went to it, she explained what it meant to be to go to a telescope. And so I get to do the very same thing. She inspired me to do this. So Palomar Observatory has a very old style lodge, so there's not a great picture of it because I took this picture and I couldn't find any better ones online. So forgive me, but imagine it's this beautiful cream building and there's a set of dorms on one side, a set of dorms on the other, and the bottom floor are these beautiful wooden lodge type locations. So you have like an old school reading room, you sign in and out on, this is a chalkboard with a painted floor plan layout. So this is me signing my chalk name into the room that I wanted, and I grabbed my keys from the little board. And then for dinner every night, we would go down and eat at this table. Rumor has it that way back when, like the 60s, there would be a house dinner bell, and they would ring it, and everyone would have to come down to eat dinner with the head astronomer. It was very hierarchical. It's not like that now, but the dinners were very, very good. The chef was very nice. He showed me all the little curry powders he used to make his dinner, and I felt very much at home. So we spent all day driving down from LA. We get there, we pick our rooms, we eat dinner, and then we go take a tour of the telescope. So this is a more modern picture of that dome. People are not riding the telescope up here anymore. We stick cameras on the back and it works much better. Probably less casualties. And this is kind of what it looks like. So these are my pictures now. This is the dome right before we would open it. This is the catwalk, so like that little strip right here, that's where we're standing. And it is completely see-through. It is rickety. You could take these grates out. And I was a little scared, but mostly in awe of the sunset. There's also rumors of, in the middle of the night, astronomers taking like 30-minute exposures, which are like how long your picture are. You don't have to do anything, and just running laps. on the top of this catwalk that you could definitely drop a phone through. Like just running and running and running and running, because you need to keep yourself awake. All right, so let's talk about the observe at night. So here is our laptop with our list of targets. This is a camera that shows us what's going on sky, and this screen shows us our different instruments. And it's a lot of sitting and looking at those screens. It's not very exciting, except that it is exciting because you're at a telescope. So this is the dome when it's open. I did take a walk in the middle of the night because I wanted to see the stars. I got properly freaked out because it's very, very dark. But I was there with Anna Ho. She was a postdoc at Caltech at the time, and we're looking at transients. So transients are things that go boom in the night. I'm not an expert. Again, I snuck my way onto this project for literally just one night. But these are things like supernova and other things that blink in and out. And we're taking spectra, which is just a fancy way of saying, like, we split it into a rainbow that's very specific. And this rainbow is monochrome because we don't have fun. No, I'm kidding. So this is what a spectra would look like on that screen up there. And that's the thing we're focusing on, a slit. And this is the high-tech technology that is running this telescope. This is this very old TV. And it's basically, you can't really see it, but it's telling us where our telescope is pointing in our RA and deck, and then the air mass, which is how much air is kind of where we are. So air mass of 1 is pointing straight up, and we are at like 1.4, so we're kind of going towards the horizon. And then it was over. I had this beautiful night where I got to look at things and I got to tell the telescope operator, please point to this RAN deck, and I had no idea what those numbers meant, but I felt really cool by saying them. And I didn't know what transients were, but I knew that this was important and we were following up for somebody else, and this would be put in a paper somewhere. I was like, this feels so much better than my computer science degree. This feels like I'm part of this monument to science that this building was built for. And so my first night was like, oh, I could do this. I see why people do this. And I am exhausted and my eyes are like watery, and I definitely fell asleep on the ride back to LA, but I want to keep doing this. So now we're going to talk about Keck telescopes in Hawaii. That's the next one I got to go to. And we're going to call this the Dream Girl because I worked with Keck and I never got to use her. The Keck telescopes are a bunch of twin telescopes out in Mauna Kea, Hawaii. They're on the Big Island of Hawaii, and I do want to say that Mauna Kea is a sacred mountain to the people of Hawaii, and astronomers have not always been tactful in the way that they interact with the native people of Hawaii, and so they're continuing to have conversations there, and getting to use this mountain is a privilege that we did not earn as astronomers, but it is one of the best sites in the world for astronomy, and we do incredible science there, and so you kind of have to sit with that heavy in your heart, and I just wanted to say that so you kind of know where we're at with these telescopes. So Keck telescopes, yep, here they are, sacred mountain in Hawaii, Mauna Kea. So Keck Observatory is a 10-meter or a 394-inch diameter mirror, but it's actually made of 36 hexagonal sections. So if you're in the back, you might not see this, but there's these edges, each of these are a different segment, and there's little lines here that like delineate them. And one of the big technological leaps that allowed this telescope to happen is we got really good at aligning all of these segments. So we actually actively kind of move them to make sure that they're actually in a full curved shape that works like a single monolithic mirror would. Okay, so Keck 1 was finished in 1983, and they're like, we love this so much, we want a second one. So Keck 2 was finished in 1996. The elevation is 1,599 feet. That is very high. It is so high that people go loopy on the mountain. And if you are not good at processing oxygen, you will get an oxygen tank. I got an oxygen tank, and I'm relatively healthy. So Keck is one of the current top 5 largest optical telescopes, and it gets a little dicey with how you decide like how large your telescope is and like what kind of reflecting area it is, but it's up there. Like this is a telescope we fight to use, and so I didn't get to use it. And it's a Cassegrain telescope. So there's a split in kind of like how we design telescope. This is kind of nerdy, but University of Arizona telescopes are usually in the Gregorian alignment, and it has to do with your secondary mirror. And then the UC telescopes, which run Keck, use the Cassegrain. All right, so I got a tour though. So I work on a lot of telescope technology and algorithms. And so I was here to work with collaborators on code, but they're like, if you came all this way to work on us with like this like very in-depth weekend of coding, you might as well see the telescope. And we were like, yes, please let us see the telescope. So we got to drive up the mountain, and so it's very high up, and so it's very desolate. There's not a lot that lives here. There are bugs, so it's not easy to photograph the life that's here, but it's kind of minimal. It does look like the surface of Mars, and you drive up maybe 2 hours from the nearest town, and then you hit 9,000 feet, and there's a little gift shop, and they say, please stop here, and you'll see better if the stars here, like, don't go higher. And that's because it's actually kind of distracting to have tourism on the mountain when you're trying to do science, and like we only have one really working access road. We don't want tourists on the top of the mountain, and yeah, for many reasons. So you get high enough, also not super resolved on this screen, but this road is all gravel. And when we went up, we got a flat tire, and so we spent 30 minutes changing the flat tire of an SUV. And it was fine, and the French man who was taking us was very kind, and he was like, we were very useless because I don't own a car, but we made it up. And then at a certain point, you switch back to normal roads because you actually don't want to be kicking up dust near your telescopes, which are very fancy optics. So it's I think it's like a 20-minute drive once you hit the 9,000 feet. And this is once we're in the dome. So they did something very special for us. Normally they store the telescope staring straight up, but they lowered it for us. And so we got to see the Keck primary mirror. And you got to look right at the primary. I think that's a selfie. That's me. And these are the two people I was with. And then this is another, it's like the primary mirror, and then the primary mirror sees its secondary mirror, which is kind of trippy. Okay, the other cool thing we got to see when we were at the Keck telescope is, did anyone know that they actually do clean those mirrors? Like, it hasn't just been the same mirror coating since 1993. This is where they recoat them, and it's actually up on the top of the mountain, so they have crews that go up there and do a bunch of maintenance work, and like there's a machine shop, I think. So this is one of the mirrors that needs to be cleaned, and I know it needs to be cleaned because there's a little bird doo-doo right there, and there's me. And this is when they strip off the aluminum, they line them up here, and then these are little aluminum pellets that they then vaporize onto the surface of the mirror segment. And this deposits it very, very thinly, so it's a very, very thin coating of aluminum. And then once they do that, they're not scrubbing with soap and water or anything. It's this vaporization process. And then once they do that, they stick it back on. And so they can, these 36 hexagonal segments, they can keep replacing. This is not something we can do with a space-based telescope, but it is also cleaner in space, so you win some, you lose some. All right, and Keck was one of those things where I spent years thinking about simulations of Keck and thinking about how do we make this work better. And like, this is one of the best telescopes in the world, so if I improve how we do science on this telescope, like the instruments we use on this telescope, I impact a ton of science. And even though I didn't get to use this telescope, I do think it was a dream of mine of like, oh, I can interact with this wider astronomy community in this way that's really impactful. And like, it's kind of broad science. Like, I could do things that impacts a wide swath of astronomers. And I think that's when I really decided I wanted to go to grad school. It's like, I want to be a part of the narrative of science, and even if it's not me discovering the one thing, I want to be a part of the story that gets told in this way that's helpful. And then I found the University of Hawaii telescope, and this is a project I actually did get to work on directly, and I did get to use the telescope. And I call her the girl next door. She's also a Mauna Kea telescope. She is actually right next door to Keck, so if this is Keck, this is the 2.2 meter. She was built in 1970, so she's actually one of the first telescopes built on that site that was permanent. She's a little taller than Keck. She's at 13,796 feet, so like a little bit up the hill. And it was the last tube design, so there's a lot of flaws in this design, which is why nobody's interested in using it, which is why I, as an undergrad, got to use it. So it's called the 2.2 meter or the 88 inch, but when it was first built, it was called the Mauna Kea Observatory. And this is my team. So this is Mark Chun, he works at the University of Hawaii, and these are two grad students, and I was working on it as an undergrad, as a collaborator with Mark Chun. I got really lucky in that sense. This is us on the catwalk. If you're an astronomer and you're on a telescope, you take the sunset picture on the catwalk. You're staring at your computer, what are you doing? This is beautiful. And then this is all the tourists who are also taking the sunset pictures. We got a better sunset picture. The other cool thing, the other thing about the Mauna Kea telescopes is you stay at this lodge at 9,000 feet. 14,000 feet is really uncomfortable, so they let you sleep at 9,000, which is very kind of them. You do not have to sleep at the telescope, though some people will be taking naps. And this is our very messy control room. It is a hodgepodge of a lot of different eras of technology and development, and I got to drive the telescope a few times. Like, I put in the little commands in the very small terminal that told it, point this direction, or close the shutters, it's windy, or move. I worked on this telescope for a while, and I'm gonna be honest, remotely, we had a lot of iced out runs where the dome was iced shut. And we would sit there and look and like, do you think it's melting? Do you think it's melting? I don't think it's melting. Does someone go up there with a pickaxe? No, not today. So the fact that it was sunny and good for this run, if a little windy, was kind of a blessing. This was the only time I got to go down there because I was mostly a remote help, but delightful. This is our instrument. It's a Maca. It works to try to correct the star twinkling problem at a much wider field. And we were like, hey, if we can prove that we can do the star twinkling thing very wide, hey, Keck, would you be interested? And they were like, show us results. And we're like, we're working on it. So this is us working on results. We stick it to the butt of that tube. We kind of connect it with a bunch of things. There's a camera in here, and there's also a lot of fancy optics. And one of the least fancy optics is this thing, and this is my project. We were trying to prove that it worked at a bunch of different colors or wavelengths. So these are 4-color filters, and we didn't have a way of turning it, and we wanted to turn it throughout the night. So they would send 2 grad students up, and we would go up on a little lift, and we hit the button, and we go up, up, and we pull it out, and we'd unstick the tape, and we'd turn it, and we'd stick the tape back on, and we'd put it back in. This is not a very oversubscribed telescope. Yeah, so I just want to say that this is one of those things where you're very lucky if you get to do this, and I felt very, very lucky, and I also felt very empowered that they let me do stuff on a telescope, and I could see the results of my actions, and I could see all the work that I was doing, and I'm working on this paper, but we have results, and this is what science feels like, and I had a hypothesis and a conclusion, and like, this was a project, and I was there for it. And now we're gonna do a trivia break. So see how much you were paying attention. So, also this looked better in the font I had, but it is okay. I have a question for you. Were you paying attention? Which A, B, C, D, or E was the oldest telescope that we talked about? A, Griffith Observatory, B, Lick Observatory, C, Palomar Observatory, D, Keck Telescopes, or E, the University of Hawaii 2.2 meter telescope. You do get a sticker if you answer this right. Raise your hand. I'm looking at...
B.
Did you call it out?
Yeah, call it out.
Lick Observatory, you are right. Do you remember the year?
1880.
Yeah, you're so right.
Fine.
You get a sticker. I'm sorry, I looked at astronomy people and I was like, oh, I don't know if you're an astronomy person. So. Yes, it is B, Lick Observatory, same as that. I have another question for you. Give me a second to read through it. Which telescope has the largest diameter? Yeah, I ignored you earlier.
Okay.
Yes, Keck, so that is D. Okay, you also probably get a sticker. I'm not really in charge of that. And then which telescope is the highest elevation? Yeah. E, yes, you were paying attention. The 2.2 meter might not be everyone's favorite telescope, but it's certainly higher than Keck, which gives you very little when that is like 100 meters. But yes, you are correct. You also probably get a sticker. All right, so now we're on to the last of my list, the Magellan Clay Telescope in Chile. And I would call us star-crossed lovers. I got to do this for my grad student project. So these are very new pictures. This is actually just my last year. And so I get to tell you how much fun I've been having. So the Magellan Clay Telescope is this telescope, this beautiful telescope here. This is me and my crew. We have a very cool person who works with that telescope who has a drone. So we took this picture very surreptitiously because you're not really supposed to get drones close to the telescope because you can break them. But Las Campanas Observatories is a set of telescopes down in Chile. They are not very popular, so there is not a little thing on Google or on Apple Maps that I was looking at, but this is where roughly it is. You might have heard the Atacama Desert is very dry and it's very high. We're right on the southern tip of that. Usually when we fly in, we fly all the way from, Tucson to Atlanta, and then we fly to Santiago, and then they're like, we've overshot. So we then fly to La Serena, and we take a 2-hour drive all the way up the mountain. We love this place, that is why we do it. So the twin Magellan telescopes are 6.5 meter telescopes. You'll notice that is smaller than Keck, but one of the cool things is that they're not segmented like Keck. They're actually a single monolithic glass piece. We're able to do that based on the technology here at University of Arizona in the Mirror Lab. So that is one big disc. It's 255 inches for all you Imperial folks. So Bade is the first one. It was named after an astronomer It was the first light in 2001. Clay, who was a wealthy philanthropist, was like, I can give you more money. And so we built the second one because everyone was into twins at that time. So 2002, Clay got its first light. They're at 8,255 feet, so again, a little less high than Keck. This is one of the debates we have as astronomers. I mean, maybe the site's a little drier. Still great, guys. We still do great astronomy. Yeah, and this is the Gregorian telescope. So this is the other half of the what type of telescope debate should we be building? So here is the mountain range. So you have telescopes here, you have telescopes here. Swope was the first one. The site founded by a lady. I'm impressed. She was very, very convincing with her money that we should build a telescope here. And she came up, I think, on donkey back, or burqa. And so she used her money to build a site here, and we kept loving it, so we kept building. And then in 2002, we finally got the Magellan twins. And so I'm going to tell you actually not about the telescopes first, but of the lodging, because I think that's pretty interesting. And that was one of the things I didn't really understand when I first was looking at things. And we know the Palomar Lodge, but this is a whole different deal. So the last component is observatories. This lodge services all of those telescopes I was just showing you on that map. And not only is this lodge for us as astronomers, it's actually mostly for the people who work on those telescopes. So native Chileans who come to the telescopes for a week. It's called a turno. They stay for a week and then they go back home and they can stay wherever they want to stay for another week. That turno system is actually very common in the area for the mining industry. So it's kind of built off that. So they also live, all the workers and telescope operators and people who make everyone food all live on these little boats. And they're pretty nice. So from our dorms, we can see the telescopes, which we love because we love our telescopes. We get a desk and a nice chair and a good view and a comfy bed, which we need because we are very tired all the time. And we get really good food. So this is the lodge, this is the dining hall. This is where we all eat as astronomers. We're trying not to bother everybody, we're very kind of loud. So we eat out here. And we also have an espresso machine, which we love. We love this espresso machine. It makes us fancy cappuccinos, which we need to get through the night, because we are very tired. Okay, now I'm going to talk to you about the telescope. So this is our telescope in the beautiful light right before we're about to observe. So really, we probably shouldn't be taking the telescope picture, but whatever. You can go up on the catwalks between the two twins. Here is one of our grad students, Logan Pierce, staring off into the no longer sunset. Right there, that box right there is our control room. Here is the telescope at zenith. They're standing straight up. And then these are these little gills on the side of the dome. And you do not see this in all the other domes I showed you. I don't remember seeing them in Keck when I was there, but they're called louvers. And when we're ready to observe, the telescope operator opens them and there's this great creaking and all these gills open on the telescope and the whole telescope breathes, because the whole point of them is to cool down your telescope right before you observe, because you don't want a hot dome and a cool night. And so these louvers open and the telescope breathes and then we get to observe. And it's beautiful and you can see through them, and so they're all over the telescope. My favorite thing. So this is us bringing our funky little contraptions up to the telescope. So this is Laird and Warren and me. This is Warren being very excited that we got MagAOX up onto this platform. It doesn't matter what MagAOX is tonight, we're just talking about telescopes. But this is MagAOX stuck on the side port of the telescope, and so it gets light from the telescope here, and then does fun stuff with it. Someone else will tell you. This is the telescope. This is honestly very bright for the telescope to be open, but they like us, so they let us do fun things. And it is tradition, again, to take a photo of you at with the sunset right before you observe. And my first run, I made almost every sunset. The second run, I was very tired. I did not make every sunset, and I regret it. All right, so let's talk about observing. I actually do have to talk to you about MagAOX a little bit, but this is me at the control center. We bring a lot of computers. We have a lot of stuff going on. We basically, before I was doing big, wide twinkling correction. Now we're doing very small twinkling correction, and we're trying to find exoplanets. And we have lots and lots of people to do that. So this is kind of what our control room looks like post-COVID, post all the restrictions. We're able to have a lot of people up here. It's getting more and more relaxed each time we go down. But this is me and my PI, Jared. This is the mega desk that we bring down. This is Jalen, another grad student, Warren again. They have the observer station, so if you want to come down to see Las Campanas and you have high contrast imaging goals, you get a little desk. Sorry. And then this is the telescope observer. Laird's sitting in his chair. I don't know why. but this is where the telescope operators sit. You can't really enjoy the majesty of what that screen looks like, but it looks straight from the 90s, and they get to tell the telescope what to do. And then this is Jay looking at the different weather screens. Also our grad student. And that's what I have for you folks. This is my love story to telescopes. I get to work with this amazing crew. I get to go down to a telescope. I'm doing everything I never thought I could do. And I get to see a beautiful, beautiful big piece of glass, take novel pictures. Every couple of months I get to go down there and do that. And I think that feels like a privilege. And I know that doing the science is a privilege, and I want to put respect on the name of the telescopes we all use, because I think it's easy to kind of have them as these abstract names, but there's a lot of hardworking people who make this happen, and there's a lot of cool history that goes on with these telescopes, and I am in love with them. I think they are so beautiful. So here is a list of all the telescopes that I've loved, and thank you. I will take questions. So the question was, and it was for me, and it was a trivia question. Who was in the White House the last time it rained in the Atacama Desert? This is actually multiple choice, because I know it has rained since the Magellan telescopes have been built. Well, debatably, it depends on if you believe astronomers or the telescope operators, because they had to recoat one of the mirrors because it was dewy. But I think that was only when we had one telescope, so I think maybe George Bush? Rutherford B. Hayes. Okay, well I was not going to get that one right. But thank you. What? Okay, well I'm sorry. I don't know all the trivia facts. Any other questions? Yes.
Are you Team Gregorian or Team Cassegrain?
I'm Team Gregorian, and I'll tell you why. There's a focus point. So I don't know if we can get back to my telescope picture, but basically the big difference is if you have a focus point or not. If I'm really, really simplifying it, there's a focus point before you get to that final star picture. Okay, yeah. So if you were looking here, for everyone who, the question was, Team Gregorian or Team Cassegrain. This is kind of like a Cassegrain telescope in that the first focus is behind your primary mirror. A Gregorian telescope will actually have a focus here. It has to do with the shape of your secondary. And the cool thing about having a focus there is if you wanted to make this mirror move and you wanted to test that mirror moving, putting a focus here would allow you to do better optical tests of that, or at least easier ones. I also am at the University of Arizona, so I feel like I picked my teams. And I'm excited to work at those telescopes, but cool question, yeah. Yes?
Have you gotten the chance to observe it in any of the University of Arizona telescopes?
No, and that's a deleted slide. I'm actually going to MMT, so the multiple mirror telescope, which actually is no longer multiple mirrors. I'm going to that at the end of the month, and I'm very excited. It's kind of weird that I went to Chile before I went to an Arizona telescope, but that means I'm very lucky. But I am going to MMT. I'm helping them do technology that's similar to the one that we do on MagAOX, which is the last telescope I showed you, the instrument we work on, and I'm helping them do that stuff. I kind of got suckered into doing that so my PI can go to Japan, but I'm not complaining because I get to see another telescope and I love them, so. Any other questions? Yes, sir, here.
What's like the elevator pitch for your research?
The elevator pitch for my research is, I'm going to de-twinkle a star for you so well that we can take a picture of an exoplanet around that star. And that is as hard as taking a picture of a firefly next to a lighthouse a kilometer away. That's what I'm doing for you. Yes. Yes. Question?
How close does that star need to be?
I think it needs to be, I think we do like within 70 parsecs. But background to me, I am a computer science and physics degree. I actually only started doing astronomy classes like last 3 months, so I'm working on it. Yeah. Any other questions? Anyone who hasn't asked yet, so then I'll get back to you. Okay, yes. Oh, sorry, I just saw you. Yes.
How does your research differ from optics?
Oh, it is adaptive optics. I just never said that. I was being really cagey and mysterious. I'm sorry. I do adaptive optics research. I actually do extreme adaptive optics research. So if you look me up online, that's actually what you'll find. Sorry.
How
Yes.
bad is the light pollution in Palomar or San Jose?
So San Jose is pretty bad, and Palomar is even worse. It's the what? Oh, sorry. The question was, how bad is the light pollution at places like Palomar, that's right below LA, and then the Lick Observatories, which is right below San Jose? I never went to Lick, so I don't know firsthand, but I know places like Palomar, I think developments are creeping closer and closer, and so even the mentor I was growing up with, who worked there in the 90s, was like, yeah, this is much worse than when I was here. There's miles more development closer. I mean, it does actually impact the science that they can do there. So yeah, that's a good question. And that's why having dark skies here in Tucson is actually kind of cool, because it keeps our telescopes happy. We have a lot of them. One more question? These are great questions, guys. Thank you. Yes?
So for the imperial stands, why do you use inches instead of feet?
Because I typed meters 2 inches in my calculator, and I did not care that it wasn't in feet. Also, like the 200 inch is like the 200 inch, and the 88 inch is the 88 inch. And I think it's just so you have one number, because you get meters or you get inches. And also, I'm only slightly catering to imperial fans. Yeah. Well, thank you, everybody. I'm gonna go.
Thank you so much, Aiden, for that really cool talk. So it is now time for intermission. I am going to make the executive decision to keep it a little bit short, just so we aren't here until 10 p.m. So please be back here at 8:30. Tip your bartender, come talk to us, come buy our merch. Trivia winners, if you answer the question right, come talk to us, just tell us you answered the question, and feel free to pick out one of our stickers. I think that is it. Oh, after intermission, we will have astronomy in the news, and then Harry Krantz with our next talk.
All right.
Hey, good job. Thank you.
I clicked on it.
Okay. Well, we're about to find out.
That works. Lily, I preemptively hit the button, so we should have another 30 minutes.
Trying again. Hello, welcome back. I think I may have left that intermission a little bit too short, so there may still be people inside. But regardless, up next we have Astronomy in the News with Drs. Jackie Champagne and Danny Kolakowski. We're both postdocs at Stewart Observatory. I don't have anything more to say on that, so take it away.
Thank you, Lily. We are the Traveling Guide from Austin, Texas. That's it. See you next week. No. So I'm Jackie. This is Danny. We were a hit duo at the Austin Astronomy on Tap, and now here we are, both postdocs at Stewart. I've heard that some people have missed our little traveling comedy act, so we've got to make sure that everyone gets to hear our amazing comedic talent. So let's get started. And if I had a slide, I would put it here. It's off again. Okay. Alright, so let's get started with the glass menagerie of cosmic monsters. So I do apologize for the formatting here, it has become very tiny. On the left is a picture of space, and there's a bunch of galaxies in it. On the right is a spectrum with a bunch of features in it, and don't worry about the text, so let me teach you. Alright, so if you look out into the nearby universe, you'll see a dense spider web of galaxies connected by filaments of gas and tightly clustered galaxies. This is creatively called galaxy clusters in the cosmic web. Before all that happened, the whole universe was in a hot, dense soup. As per the theme song of the most annoying sitcom to any astronomer. But the point being, the early seeds of galaxy clusters are much more spread out, they're much smaller, and they're less webby, so they can be hard to find at high redshifts. High redshift meaning younger times in the universe. But of course, the James Webb Space Telescope lets us get a whole lot more webby, so there's no shortage of exciting things found by the GLASS survey, the GRISM Lens Amplified Survey from space. It's a good one. We hate tortured acronyms in this house, but that's a good one. That all the letters go where they're supposed to be. But let's get serious. Okay, the progenitors of the super dense galaxy clusters in today's universe are creatively called protoclusters, and we find them mostly by accident. So one way to hypothesize that a bunch of galaxies are close together or connected is by comparing their colors using photometry. So that involves taking photos in different wavelength filters. And galaxies that are close together might have similar colors, but the point of doing this is not so much to find similar ages, but to look for this dropout band. So this is identifying the wavelength where hydrogen eats away all of this blue light, and that tells you roughly how far away it is in time and space. I know that that means absolutely nothing, so just bear with me until we get to the pretty part. What else? So this team previously hypothesized that we were seeing a galaxy protocluster located at redshift 7.9. So that is roughly 650 million years after the Big Bang, and this is based on their photometric properties. So that's what we're looking at here on this left image, is a bunch of galaxies that have very similar red colors that are very close together on the sky. But that's a hypothesis. The gold standard is by getting a spectrum, looking at these atomic and molecular features. So the unmistakable signatures of elements like hydrogen, oxygen, carbon, etc. can tell you precisely where a galaxy is hanging out. And so lo and behold, the GLASS survey did indeed confirm the existence of a galaxy protocluster that contains 7 galaxies in a tightly packed space of 400,000 light years across. So that is about putting 6 galaxies in between us and Andromeda. They're very close together. And so at right, we're seeing these spectral signatures of a hydrogen line over here, and the doublet of ionized oxygen. And this is of one particular galaxy. I don't need to show you all 7 because they look mostly the same, and that is really cool for learning about how galaxies are connected to each other and how they evolve in similar environments. And so looking at this evolutionary state, for example, from the spectrum, we can see that hydrogen is being eaten away. So I said something about a dropout band before. So you'll have to imagine it. Here all of this light is being eaten away by neutral hydrogen, and so you can imagine if you took a picture that was a filter at this wavelength, you wouldn't see anything at all. And so that gave us our hypothesis, but now we see unmistakably that that hydrogen is being eaten right at that precise location in the universe. Another thing is that the galaxy is very blue, so it's brighter in these shorter wavelengths, and that generally means that it has young stars, so those stars have formed recently. And the galaxy has a ton of metals in the interstellar medium, so that space in between stars, which is shown roughly by the very strong oxygen signature. So the high amount of metals is particularly surprising since we generally don't expect them to form until a bit later in the universe, so that implies that there is some rapid enrichment happening. And so further details are beyond the scope of this talk, which is a favorite phrase that people use in their papers, especially me, to mean I don't have the time or desire to do any more work on this topic, therefore what I said is correct. But this is an extremely exciting discovery to find these signatures of galaxy clusters. So again, this is 650 million years after the Big Bang, so it is less than the time it took for dinosaurs to evolve.
There we go. You know, I think I said this exact same thing the last time we did the news here, that like the worst part about JWST is that it's making it a lot harder for me to make fun of y'all galaxy people with your like 1 point spectrum at a signal of 5. That's actually pretty nice. You know, so I'll give you that, right? Okay, so moving on. So I know here at Spacecraft we say choo-choo, but how about this time we say juice, juice? Yes, I said juice, not what you drink, but I guess what we blast off to Jupiter. So I've only done the news here one other time, so this is number 2, and here is 2 for 2, another installment in the lesson of if I'm on this stage telling the news, I will find a way to talk about the icy moons of the outer solar system. So here we go. So very excitedly, about almost exactly a month ago, the European Space Agency's JUICE mission, the Jupiter Icy Moons Explorer, it's not an acronym. It used to be an acronym, and then they just said, you know what, we're just going to call it JUICE, which I respect that. Not every letter needs to be capitalized. So a month ago, this mission launched on April 14th. It won't arrive at Jupiter until 2031, so we got a little bit to go. It does some fancy little gravity assist shenanigans to blast off to Jupiter. But this is a super exciting mission that the whole goal is to kind of orbit Jupiter and study in detail 3 of the Galilean moons, the icy moons Ganymede, Callisto, and Europa. And why those moons are so cool and interesting is that they all likely have oceans of water beneath their icy crusts. And of course, as astronomers or planetary scientists or whatever, we hear water and it's like, oh God, maybe there's life. Great. So we want to find out more. So the main objective of this mission when it reaches the Jupiter system will be to, 1, study Jupiter's environment. So Jupiter itself has a very, very strong magnetic field, and that very strong magnetic field and then kind of radiation and particle environment can affect the moons that are orbiting close by, like these Galilean moons. So this will teach us more about that, and then also study the moons in detail to determine their structure, kind of try to back out how they have formed and evolved, and then of course inch closer to answering the question whether or not they could be habitable. So how will this mission do that? It has a very impressive 10-instrument payload, and this includes multiple cameras, multiple spectrographs, which will kind of take images of the surfaces of these moons to learn about them. They have a magnetometer, there's a radar sounding instrument, there's a few others that were words I didn't even know, so I'm not mentioning them here. So what will happen is it will enter Jupiter's orbit around Jupiter. It'll do, I think, something like 30 to 40 close flybys of these 3 icy moons. And then after that, it will actually enter in an orbit just around Ganymede. Out of these 3, Europa's the one that you're probably going to hear the most about. Like, yeah, it definitely is probably the coolest. But Ganymede is also really interesting. It's Jupiter's largest moon. It's actually the largest moon in the solar system. It's actually larger than Mercury. So that's pretty cool. Like I said, it has a subsurface ocean, and it actually has a tenuous atmosphere, and it has its own magnetic field. So all of these things make it quite unique in terms of what a moon can be in our solar system. And so this mission will return very detailed surface maps. It'll teach us about the 3D structure of these moons, so how thick are their crusts, how kind of deep are their water oceans, how much water do they have underneath them, and kind of all of this is important to, one, plan future missions to maybe land on these moons and actually maybe drill down and learn more about what's going on, and then of course learn more about potential habitability. And pretty excitedly, so JUICE will be there starting in 2031, and around the same time, NASA's Europa Clipper mission will also be there, which will be focusing on Europa. So these two satellites will be kind of dancing together, teaching us about the Jupiter system. So I doubt I will still be here doing the news in 2031, but I hope whoever is shares my enthusiasm for this topic, and that they can teach you all about what these awesome missions will tell you in the future.
Thank you. That was quite the love letter to the Jovian moons. I'm surprised. Exactly. But would you say that they're cooler than the Saturn moons? What about Enceladus?
We don't play favorites anymore.
Okay. What would I know? I look at things, less than dinosaur old. Okay. Meteorites. So, if a rock came crashing through your window, you, a sane person, would probably assume that some mischievous kids took a prank a bit too far, and you, a sane person, would definitely not assume that an extraterrestrial object had made its way through the Earth's atmosphere, through your roof, your ceiling, and then bounced around your walls, turning your house into Swiss cheese. Except this exact situation did happen last week at the address of Susie Kopp, who's definitely not a cop, in Hopewell, New Jersey. And my home state is known for a lot of iconic things, like bagels, pizza, Bruce Springsteen. But I don't think that I expected a meteorite to come dancing in the dark. Maybe if Susie had yelled, "Cover me," then the rock, which was not born in the USA, might never have reached the promised land. Wow. Thank you. So after reporting this incident to the Hopewell Police Department, who is the source of this image, this is evidence, the Fuzz took the strange, still hot rock into custody to investigate further, since there was no evidence of a human being anywhere near the scene of the crime. Emergency responders did come. They checked that the rock was not radioactive, but it was very dense, 2 pounds and only 6 by 4 inches. Seemed pretty peculiar for a normal rock, so it was eventually turned over to the College of New Jersey's physics department. And so then, together with meteorite experts from the American Museum of Natural History, they hypothesized that it was a meteorite in the stony chondrite family, meaning that it is non-metallic material made up of dust grains that formed in the solar system. Such meteorites are commonly found on Earth, making up 85% of all meteorites that survive crashing through the Earth's atmosphere. A lot of them just burn up, but some of them do make it to the ground. But most of them actually hit Antarctica for whatever reason. I don't know, there's a lot of land. And so using a scanning electron microscope, which is the thing that I've never gotten to touch, so it sounds pretty cool, they determined that the rock was an LL6 meteorite, meaning that it is less iron-rich than other meteorites. It also makes it 30 to 40% denser than granite or slate, and its overall chemical composition is unlike any rock that can be formed in Earth-like conditions. So this is definitely confirmed to be of extraterrestrial origin. But unfortunately, a lot of its chemical fingerprint was destroyed due to the friction of coming through Earth's atmosphere, so it kind of burned and melted the outsides. So for now, we had to just be satisfied with the fact that it's probably not aliens, but it definitely came from space. And so in honor of one of the first meteorites to hit New Jersey in modern history, it was colloquially named Titusville, after a nearby town. I'm from there. I've never heard of Titusville, so it's a really stupid name. So here's my list of things they could have called it. Rocky Soprano. Whitney Houston, we have a problem. Rutgers University. John Bunn Stoneby. Or even the very obvious Stone Pony. If you know, you know. Okay, that's the end of my New Jersey bit. I'll be back to have more jokes about cosmic bagels or something next month. And here's Danny back.
Okay, wait. You said, so it's named Titusville after a nearby town, not the town it fell in?
Correct.
Okay, and you wonder why people make fun of New Jersey.
Yeah, that's the reason.
Well... Whoa, whoa. Oh no. Well, that's... there we go. Yay. That was very strange. Okay, so if you ask an exoplanet scientist kind of why they do what they do, I feel like more often than not you'll get some riff on like, oh, la la la, life is out there somewhere, let's find it, right? Then you might follow up and be like, okay, well, how are we going to do that? And that is a question that we all then run from. But kind of, two of the things that you'll probably hear most about as an exoplanet scientist to learn about potential life elsewhere in our galaxy involves the presence of an atmosphere or the presence of water on another planet, both of which, at least in our very limited view of a data point of one habitable planet, are very important for life. Okay, so if we want to find life, let's go find water in an exoplanet atmosphere. Super simple, right? No. It's very hard to do. Kind of our understanding of atmospheres of rocky exoplanets is very, very limited, if we have any at all, confirmed. But this is where our new favorite telescope, JWST, can come in, which is actually capable of detecting some important molecules, including water, in the atmospheres of other planets. And so in one early program by JWST, led actually by a scientist out of our own LPL, Dr. Sarah Moran, what they did is they pointed JWST at GJ486, which hosts a roughly Earth-like planet. It's a bit larger than the Earth, to look for an atmosphere. And so what they do is what's called transit spectroscopy. So as a planet passes in front of its host star, and we're observing it, it'll block out some of the light. And if that planet has an atmosphere, that atmosphere will also block out some of the light. And depending on what's in the atmosphere, it will leave imprints on the starlight that we're able to observe that correspond to specific molecules like water. And so what they did is, so this is the spectrum. Okay. Yeah, well, juice. And what they see, it's a little hard, but there's this little kind of line going up here. And that's pretty definitively from water. So that's really cool, right? Damn, they found water in an exoplanet atmosphere. That's Earth-like, great. Well, maybe not great. This is a little strange, so I tricked you. I said GJ486b is Earth-like, which is true that it's just a bit larger and more massive than the Earth. But it's also orbiting its host star, which is a different type of star. It's a cool red M dwarf, but it orbits it in about a day. So it's really, really hot. It's like 100 degrees Fahrenheit on the surface of this planet, which, I mean, I love a good spa day, but I think that's a bit much of a sauna for me. I'd rather not burn up and die. So that's a little weird. We wouldn't expect a planet this close to its host star and that hot to retain any sort of atmosphere, particularly for these cool red M dwarfs, which are very, very active. They're throwing off a lot of high energy radiation that would likely erode atmospheres fairly quickly. So if this water really is in this atmosphere, that's a paradigm shift in our understanding of these atmospheres and how they form and are maintained, because it would have to be constantly replenished so that the star is not blasting all of that water off. So that's really cool. But there is a pretty large caveat here. That might not be from the planet itself. So these types of precise measurements by exoplanet scientists, it often has to be kind of sifted out through nuisance stellar noise, which I'm a stellar astronomer, so I might switch which is the nuisance there, but I guess the water's kind of cool if it's on the planet. But it's actually possible that this water is being detected, but on the star itself, in star spots that are really cool, well, relative to a stellar surface, they're cool, and can actually have water in them. So, unfortunately, while they have definitively detected water in this spectrum, they can't say whether it's from the planet or the star, And so more observations are necessary and planned that can actually be taken with JWST at both longer and shorter wavelengths than they observed to find out whether the water is coming from the planet or from the star. Obviously, if it's from the planet, that's way cooler, but I still think it's pretty cool if we're detecting the star too. Yeah, so pretty cool. Thank you. That was a mistake.
Mind the gap.
Rip.
Thank you so much. So now, up next is our second and final talk of the night from Dr. Harry Krantz, who will be telling us about a sky full of satellites.
Hello, thank you everyone. So I see a few familiar faces out here, so a lot of you may have already seen parts of this talk before, but to summarize, essentially I'm talking about the new constellations of satellites, namely Starlink. I'm sure you've heard of Starlink before, but namely what these constellation satellites are and how they're going to affect astronomy going forward. Hence the name of my talk, A Sky Full of Satellites. Maybe? Oh, there we go. So, let's see, actually. Back one?
Is the battery finally dying?
Are we missing? Oh, there we go. Third time's a try. Alright, so here we have a fun little cartoon diagram showing what is going on. So, we have our Earth there. We have a satellite up in space doing a nice little orbit around Earth. And when this satellite is in orbit, it's being illuminated by the sun. And that sunlight reflects off the satellite, and it can be observed by someone down on Earth if it happens to be nighttime where that person is on Earth, but the satellite's above the person on the ground and can still be illuminated by the sun. And now's the part where I was hoping we might be able to do a fun little demonstration and spot some satellites, but the clouds are a little bit thick tonight, so I'll just tell you, on another evening when you have a little bit more of a clear sky, go ahead out a little after sunset, look up in the sky, and I guarantee you, you will see a satellite. To your eyes, it will look like basically a star, but it's going to be moving across the sky. However, if you are an astronomer, this thing has a very long delay. There we go. If you're an astronomer or photographer and you're trying to take a picture of the night sky, you might see a satellite like this. You'll take a picture of something like here, the Orion Nebula, but that satellite, as it's moving across the sky while you're taking your picture, is going to leave a trail, a line, or a streak, essentially photobombing the night sky. And if you're a professional astronomer trying to do research, well, these can be a real nuisance because the satellite trail could do things like obscure, block the thing you're trying to look at. It might also block things like nebulosity, galaxy structures, and it can cause other effects with the detectors. It can do false transient triggers, all kinds of different effects that these satellites can have on research astronomy. Maybe. Let's see. This thing's not working. I'm just going to tell you to move slides if that's okay. Go ahead and go slide.
Easier said than done. What? No.
So the thing is, it's changing on OBS.
Yep.
It's just not
this is
changing
an
on
OBS
this.
thing. That's fun. Okay.
No, it's a PowerPoint thing.
Oh.
Because it's same thing here. I change it. There we go.
This is bizarre.
There we go. So we're going to go ahead and go to our first trivia question here. How many satellites are in Earth orbit right now? And just, there's an asterisk there. You can't really read that small text. We're counting satellites. These are things that we intentionally put in orbit. So payloads, satellites, rocket bodies. We're not counting debris objects, fragmentation stuff. These are satellites we've deliberately put in orbit. So I'll go ahead and see. Anyone raise their hand? Anyone want to make a guess here at the number of satellites in Earth orbit right now? We've got a hand.
Over 20,000.
Incorrect. We got a hand in the back.
10 to 20,000.
Correct. I think you get a sticker. Lily's in charge of that. Let's see, maybe the clicker will work?
It worked. It's a PowerPoint thing. I don't know what to do about it.
Alright, well, that's okay. We don't need to see the answer. The correct answer is 12,861, or at least that's the number when I calculated on Monday. There was another launch of Starlink satellites on Monday, so that number's already out of date. But we're in that 10,000, 20,000 range. And the important thing on this plot, though, is showing the number of satellites over time, since Sputnik in 1957 to the year today, 2023. You can see how the number of objects has gradually increased, and in the last couple of years, that rate of increase has really sped up. Just in 2017, there's about 6,000. So in the last 5 years, we've more than doubled the number of satellites in orbit compared to the previous 50 years. So this is really an unprecedented time of space development. And of course, this is primarily being driven by the new large constellations of satellites, namely Starlink and OneWeb. So here's just a little overview of Starlink and OneWeb. I'm sure you've heard about Starlink, OneWeb less people have heard about, but both of these are very large constellations of satellites in low Earth orbit. Both are trying to do high-speed internet worldwide without having a wire connection on the ground. Starlink has just over 4,000 satellites in orbit. They have plans for up to 42,000 total satellites, though. So we're only at 10% of what they might end up actually having in another 10 years or so. These are in a 550-kilometer orbit, so again, we're talking in low Earth orbit. They have this kind of interesting design. It's kind of a flat chassis, kind of about the size of a picnic table, and then this large solar array that extends above it. OneWeb has about 600 satellites in orbit right now. They have plans for up to 7,000 satellites over the long term, and these are in a higher 1,200-kilometer orbit, which we'll get to why that's important a little bit later. They have a more traditional satellite design you might have seen, a central box-shaped chassis. We call this a box wing design. You have the box and the two solar panel wings extending from either side. And this is about 1.5 meters for that central chassis, and then the solar arrays are about a couple meters each. This is fun.
Yeah, it's. I don't know why. Let me try something. See, that's correct.
Okay, yeah.
Which one do you want?
Go to that one. Oh, we skipped that one, that's okay. Go to the... That guy. There we go. Alright, we'll try this. So, like I was saying, we have Starlink and OneWeb, but these are only two of many expected constellations of satellites, of companies, governments around the world who have said, hey, this satellite internet stuff is really big, we want to do this as well. So while Starlink and OneWeb are really leading the way, we have an entire list, and this is an outdated list I should mention, we have an entire list of constellations that are expected around the world. All these are in low Earth orbit. All of them are expected to be brighter than the previous era of satellites, which is primarily in higher, either mid-Earth orbits like GPS or geostationary orbits. This is really a concentration of new satellites in low Earth orbit. So I pose the question that it's a question of when but not if are we going to see 100,000 satellites in Earth orbit. At one point in time, we were talking about maybe by 2030. I don't know if we're going to hit 100,000 by 2030, but again, it's a question of when, not if. That's working pretty well. Of course, lots and lots of new satellites. This vastly increased number of satellites brings a lot of new challenges. You can think of some obvious ones like space traffic management, how you keep these satellites from crashing into each other. But there's a lot of other things that we haven't really thought about before, and we haven't really thought about until this reality was faced in front of us. Some of these have to do with launch and disposal. So we launch these satellites. Well, rockets make a lot of pollution when they launch, depending on the kind of rocket fuel. And when you only had a couple rocket launches a year, it wasn't really that big of a deal. But now you have almost daily rocket launches. People are suddenly wondering, what is the atmospheric pollution effects of this? And likewise for disposing of the satellites. When we dispose of a satellite, we do that by burning it up in the atmosphere. So again, people are starting to question, well, if you're burning up thousands of satellites every year, what does that do to Earth's atmosphere? What do these metals that are being vaporized do in the long term? And then, of course, the last bullet point here is what we're going to mostly talk about going forward here, is the incidental effects on astronomy, and that is the incidental photobombing, these lines and streaks appearing in astronomical photos, either for astrophotography, amateur purposes, or professional research. Now we're back.
So now it's working here and not on our live stream. I'm so sorry. Would not be space drafts without technical difficulties.
Absolutely.
It'd be a good time for a train.
Yes.
All right, let me. Now try advancing.
PowerPoint.
Oh.
Attempt.
Hey, that's reacting. Okay, so back to where we were. So satellite impacts on astronomy. So seeing a satellite in your images isn't a new thing. Satellites have been in the sky since the 1950s. And we've seen satellites, and ask any astronomer, even astronomers from 30 years ago, and they'll have described reports of seeing satellites. Maybe if you were a child 20 years ago, you might remember seeing a satellite one evening and then waiting an hour maybe to see another one. But this is changing now because we have significantly increased numbers of satellites. What I'm talking about here is a numbers game. This isn't a new phenomena, but the phenomena is becoming increasingly more common. So with more satellites, we're more likely to see a satellite. The satellite's therefore more likely to obscure a target if you're doing professional astronomy. And this leads to rejecting more images, more work to recover those images for data purposes, and ultimately more observing time and more research funding in order to actually complete a project which could have been easily done 10 or 20 years ago. So now our second question, who governs space? A, NASA, B, the FAA, C, the FCC, D, the US Space Force, E, all of the above, or F, none of the above. Any hands? Correct, none of the above, which is a little bit of a trick question because all of these agencies do kind of regulate space, but at the end of the day, no one really governs space. We don't have a body that says, send us an application and we'll give you an orbit. You kind of just do it. And to summarize this, I have a quote from a report to the NSF by the Jason Advisory Board. A company who wanted to launch a dump truck full of sand into the same orbit as the International Space Station would have no formal barriers to doing so in many countries around the world. In a nutshell, this really summarizes the current state of space law. It is kind of the Wild West. You can do what you want if you have the capability to do it. Some people might shout at you, and maybe someone needs to do something to push the buttons and we'll get some regulation formed. But right now, this is where we are. So as far as astronomy is concerned, there's no regulations we can point to and say, hey, we should regulate how many satellites are being launched, but maybe that's going to change in the future. So over the last couple of years, there have been several international discussions, which I've been privy to, talking about these satellite constellations and how they're going to impact astronomy and, well, what can we do about it? We have a couple of key conclusions that I'm going to list here. First one, the satellites are not going away and more are coming. Like I said, there's no regulation that we can say just slow down the launches or any way to regulate that. It's happening, we have to accept that. Second point here, there is no mitigation which will fully eliminate the impacts. If the satellites are in the sky, they're going to be visible, they're going to appear in your images, they're going to appear in your data. There's nothing you can do about that. We just have to do the best we can with the reality we have. On that note, the best solution is going to be a combination of mitigations. There's no silver bullet. There's no way we can just say, we're going to do this and everything's going to be the way it was. It's going to be mitigating the impacts as best we can. There's a recommended 7th magnitude limit that was set in one of these meetings, which we'll get to a little bit why that might not be the best way to do things. But there's a recommended 7th magnitude limit, which also is the naked eye magnitude limit. So at least as far as humans wanting to go sky gazing, that's a good target to shoot for because that means they would be invisible to the human eye. And the last one here is mostly what we're going to talk about is the need to monitor the situation and prepare for the future. we can't come up with mitigations and solutions if we don't know what the reality is we're facing. On that note, also, all these meetings we've had over the last couple of years have culminated in the newly formed IAU Center for Protection of the Sky. This is a coordinated group that I'm a part of, trying to basically coordinate voices, making sure everyone's actually working together, no one's going off on their own and doing something that's counterproductive to whatever else is trying to accomplish. And I'll point out, if you want to know more about this, if you want to get involved yourself, you can go to the IAU CPS website. You can even apply for membership. So all this brings me to what I did for my dissertation research, which was a photometric survey of these satellites, essentially trying to measure how bright they are, to answer this key question of how bright are these satellites? And that's a very important thing to answer, but it's a very tricky thing to answer because satellite brightness is not as simple as many people would realize. Unlike stars or other many typical astronomical objects, you can't just point your telescope at it, make a measurement, and say, well, there's the number. If you point your telescope and take a measurement of a satellite, say pointing over here, take another measurement pointing over there, you're going to get a vastly different answer. Even if you look at the same satellite in the same part of the sky, your answer is probably going to be vastly different depending on when you looked at it. So in order to measure these satellites and come up with a comprehensive characterization of their brightness, we really need to observe lots of satellites across the entire sky in all geometries and times, basically all the situations astronomy might observe a satellite. This is our little telescope. It is a purpose-built system for observing satellites. It's in a mobile observatory, though it mostly spends its time up on Mount Lemmon, here just north of Tucson, Arizona. It's not a very large telescope, but has a very large field of view, almost 4 degrees across, which is much, much larger than many professional observatories. And this is good for looking at these fast-moving satellites, because you can't catch them very nicely with a small field of view, because their position errors have a little bit of uncertainty on them. To summarize the photometric survey before we get into the results, we operated it for a little over 3 years. We're currently in a technical upgrade phase, so we're not observing right now. We have over 16,000 measurements of over 2,800 individual satellites. This is what the data looks like in a nutshell. So this is a what I call a sky plot. So this is looking directly up at the sky, projection of the sky. You have north, east, south, west. Each of those colored dots on the sky is where we observed a satellite, and the color represents how bright it was. And around the edges here, below the shaded horizon, that is the position of the sun for every one of those measurements we made. And you'll note that the sun is not in the same spot for all these measurements, because we're doing these measurements throughout the seasons and at different times of night. So the sun moves. And so that means the geometry for each of these measurements is not consistent. So what we need to do is rotate each of those plotted points around the center point, around the zenith, so the sun's always at the same azimuth. That maintains the geometry that we're trying to get to. And when we do that, we find these very interesting patterns of brightness across the sky. So I'll run through these a little bit. Is this the laser? Well, I don't know which one's laser. There we go. So we have a couple different populations of satellites here. We'll start here on the upper left. This is Starlink version 1.0. This was the first production version of Starlink satellites that started launching in 2019. They have a median magnitude of 5.7, but they have a range of, 4.5 to 7 magnitude. So that's a very large range of brightness. And you can see how that brightness distributes on the sky. It's mostly kind of brighter towards the zenith, and then it kind of gets dimmer towards the horizon. But you can see that across pretty much the entire sky, it's far above that 7th magnitude threshold we're trying to reach. SpaceX has been very kind to the astronomy community, has implemented changes to the design to try to reduce their apparent brightness of their satellites. One of these was what they called the visor sat design. So they added these visors that hang down under the satellite to try to block the sunlight from hitting it.
Should have gone to the sandbags.
Oh.
That was exciting.
Didn't expect that to happen.
sorry. You've been having such.
New job. All right.
Such an
So
eventful.
we were talking about the visor sats. So they added these sun visors to try to reduce how much light reflected off the bottom of the satellite. And you can see readily with this sky plot how much of an impact it really had compared to that first version of Starlink satellites. It also dropped the median magnitude from 5.7 to almost 6.9. So we're getting really close to that 7th magnitude threshold. However, I'll still point out that the range of typical magnitudes here still goes as high as 5.25. So not all of the satellites are below that threshold. And when you look at the plot, you can kind of see that, well, it got really dim on this side that's near the sun, but opposite the sun did not. It's almost exactly the same brightness as it was for the first version of the Starlink satellites. I'll explain why that is in a future slide, but we'll keep going through here right now. Version 1.5 of the Starlink satellites, they actually removed the visors because this was the upgraded version of satellites. They added lasers for inter-satellite communication, which is very cool on that side of things. But unfortunately, the visors blocked the lasers, so they had to remove them. Though they didn't implement a number of other smaller changes, material changes, surface changes on the satellite to try to reduce its overall reflectivity. So it's not as dim as the visor sats. Our median is now 6.1. But these small changes did improve over that first 1.0 version. And again, you can see how the pattern on sky looks. And then for our complete set, we have OneWeb, which has a median of 8.2, so below that 7th magnitude threshold. And that's primarily because, like I mentioned, these OneWeb satellites are in a much higher orbit, 1,200 kilometers instead of the Starlink 550. So just being farther away, they tend to be dimmer overall. And they don't have as much distinct pattern across the sky. You can see a little bit of brightness here near the zenith and a little bit near the sun. So trying to understand satellite brightness, it's all about the reflecting geometry. So it's about, well, where are you seeing the satellite in the sky and how does that correspond to how you're looking at the satellite? Which part of the satellite are you seeing? And to just demonstrate how much of an impact they have, I have this little clip from another project of mine. This is EchoStar 2, which is an old defunct communication satellite at geo orbit. It is no longer actively maintained, so it's spinning. It's just randomly spinning in space. And in a fraction of a second, this is a real-time video, it goes from 13th magnitude to -1 magnitude. So that's 14 magnitude changes of brightness in a fraction of a second. All because we're looking at the satellite at a different angle. So now you can kind of understand how you're seeing such a vastly different brightness depending on where you see the satellite in the sky. So I'll bring us back to our little cartoon drawing here. But I'm going to tell you right now to forget this drawing because the key word here is not to scale. For these satellites, they're so close to Earth, their low Earth orbit is so low, it's more intuitive to think of the Earth as being a flat plane and the satellite going across just horizontally, like an airplane. And we have our sunlight coming here from the right side, hitting our satellite, and let's see how it might reflect. So I'll start over here on the right. You have sunlight coming in, you have this bottom side of the satellite, which is basically horizontal. You have a really good geometry for some forward specular reflection. And we see that in the sky plot. We see this bright hot spot near the horizon close to the sun. Going overhead, we don't have any obvious reflecting surfaces to make really bright reflections. So instead we kind of get a random scattering of light, what we'll call a diffuse reflection. And you kind of see that in the plot here. There's no obvious area where there's light being hot spotted. Then we get over here to the left side. Now we see a lot of backward speckled reflection coming off of the solar panel, which is basically a vertical plane here. And we see this on our plot here as the broader hotspot opposite the sun. And of course I mentioned those visors would be hanging down. Well, those visors work really well for blocking the forward specular reflection, which you can kind of see here, these really dark red areas. But that visor actually increases the reflectivity when you get opposite the sun. You actually have a longer, larger area to reflect in terms of backward reflection. So I hope that kind of gives you a little bit more intuitive understanding of why we see these patterns depending on where you see the satellite in the sky. So some solutions and mitigations, like I mentioned, SpaceX has been very kind and has changed their designs several times now to try to improve how it is affecting astronomy. And overall, their design changes have yielded about a 50% reduction in overall brightness in terms of linear reduction. However, to reach that 7th magnitude goal based on their best solution, you need another 84%. And I'm not a satellite engineer or spacecraft engineer, but I've worked with some, and I know if you go up to them and say, good job, you've reduced the reflectivity by 50%, we need to do that 84% more on top of what you were done, they're going to tell you to take a hike. It's not really possible in terms of spacecraft design. There's still room to be had, but at the end of the day, like I said, the best solution is going to be a combination of mitigation. So we really commend SpaceX for what they're doing, but changing the satellite is not the only option. The astronomers also need to do their homework here as well and start looking at what they can do on the ground to improve things overall. This includes things like new software tools and image processing methods. One that I'm really interested in is strategic scheduling of observations. This could be to try to avoid individual satellites. We know where the satellites are going to be, so if you know there's going to be one where you're trying to observe, you can strategically avoid it. You also can look at the sky plots I just showed you and say, well, we know the satellites are not as bright over here, so let's look over there instead of over here. There's other things we can look at, hardware improvements. You can use fast shutters to try to block the satellites, light from even reaching the image plane without actually stopping the data collection. And just overall improved instrument design in order to accommodate bright satellites. We're seeing a lot of secondary effects on the sensors because they design them without thinking about satellites and how they might impact the sensor. So just a conclusion slide here. Big point here, this is not a simulation, this is real data. A lot of people have been working on this problem, but no one's come up with a data set quite as comprehensive as this. And a lot of people are getting the answer wrong, in my opinion, with their simulations because they don't really cater to all these small nuances in terms of reflection geometry. Satellites are going to make astronomy more difficult. Not impossible, but more difficult for sure. So we really need to be looking forward of, well, what are we going to do in order to mitigate this, improve the situation overall, and make sure this doesn't come as a surprise to anyone on the ground doing astronomy. And then the last thing I'll just mention here again, the best solution is going to be a combination of possible solutions. There's no silver bullet. Everyone needs to do what they can do individually. And if you have a really creative idea, I encourage you to work on it or talk to someone who can work on it. Get involved with the IAU CPS. If you have a really good solution, you could hopefully make a job or even money out of it. So with that, I'll end my talk here, and thank you very much. Any questions?
Is there any international meeting to discuss organization?
Yeah, so the question is there any international meetings or organizations kind of working on this? And the short answer is yes, there's lots of fronts this is being pushed. So like I mentioned, we've had some international meetings just among the astronomy community, which then began the IACPS, which is an international organization. And through them, there's actually an effort working with the United Nations COPUOS group, which is the space branch of the UN, to see, well, could we actually have an international agreement at the United Nations level on this, which is a very far-fetched idea and very slow-moving, but the fact that they're even catering to this and this is on the table is a very good effort. Yes?
How does this affect other wavelengths of astronomy?
So yes. I only talked about what we'll call the optical here. So repeat the question. Yeah, so how does this affect other wavelengths of astronomy? So I only really talked about optical, and this also mostly applies the same to infrared. Of course, the brightness is different in infrared. It's actually brighter in infrared usually than optical wavelengths. But then you have things like radio astronomy, which is a whole different ballgame. And the interesting thing is radio astronomy has been dealing with satellites much more severely, much longer, because essentially these satellites are large, bright objects broadcasting radio wavelengths in the sky. So radio astronomers have dealt with this a long time, but they have it even worse because it's a lot harder to avoid them in the sky than we do, and they get them 24/7. We only see these satellites during twilight hours when it's dark where we are, but the satellites are still illuminated in the sky. I don't know enough about radio personally to know what the solutions are on that side, but I know we're talking about just as much as optical in terms of what we're doing with the CPS group.
Hi, we have a question online from Andrew asking, is there a source of satellite elements accurate enough to allow an observatory to schedule their shutter openings to miss a satellite passing?
So the question is there a source or a way to know satellite positions accurate enough in order to either avoid them or close a shutter on a telescope? It depends on your field of view. It's a complicated thing to answer. The short answer is yes. We know the positions of all these satellites very well. within an Archimedes or so ballpark range. So for the majority of purposes, for the majority of satellites, I think yes, you could pretty easily do it. However, it does become a computationally hard problem with more and more satellites. I can currently run a computation to compute the positions of all the satellites on my laptop for one point in time, and it takes about 10 minutes. So you can imagine doing this for all the times during your entire night, and it becomes a very computationally hard thing to do. So in my mind, the answer is not necessarily to try to avoid individual satellites in a predictive manner, possibly doing it in a reactive manner by having a secondary telescope that's looking co-aligned with your main telescope, and if that telescope sees one, it triggers something to close. Otherwise, I think it's going to be much more strategic to think of this as essentially having a cloud of satellites in the sky and saying, well, where do we minimize the impact instead of trying to individually avoid satellites? Any other questions out there? Yes?
Can you use some type of interferometry?
Can we use some type of interferometry? I don't know. I don't know how that would necessarily apply here. Certainly not for avoiding them, though. I suppose. Are you going more of like using multiple aperture, or?
I guess I'm thinking of. I'm thinking of the radio regime.
Ah, yes.
You can kind of integrate that stuff out. I don't know how to solve it.
Yeah, I'd have to think about that. There might be something there, but I'm not sure off the top of my head. Any more? Last call. Yep.
Is there just to prevent them from running into one another, it wouldn't really help astronomy, but is there an absolute separation for geosynchronous?
So the question is along the lines of well, how do we keep them crashing into each other? Is there a separation between their orbits? Is that correct?
Yes.
All right, so this comes back to, again, a little bit of the space regulations of, well, you really play a game of chicken. So you have two satellites, and we have a lot of groups on the ground, including the US government and many private companies whose entire job and industry is to keep track of these things and say, well, when are they going to come close together? When is there a possibility of a collision? And if there is, they notify the owners of the satellites and usually charge them money. But essentially then you say, well, we have two satellites that are coming close to each other, and we have about 12 hours before this is going to happen. It's called a conjunction event. And usually what happens is then they play a game of chicken, because moving a satellite uses fuel, and that ultimately reduces the life of your satellite and how many years you're going to get out of it before it runs out of fuel. So you kind of come to this point of, well, who's going to move their satellite first, company A or company B? If it's A is NASA, they have precedence. There is actually some enforcement there that anything NASA owns usually takes precedence, and so the other satellite has to move. But if it's, say, two private companies, like, say, a Starlink satellite and, I don't know, a Planet Labs satellite, then it really comes down to, well, who's willing to risk it more? Because they all have risk tolerance thresholds on what they're going to do. And so that's one of the things we need to look more towards with regulations, is establishing right of way and establishing, well, who's going to move when and who establishes precedence. Otherwise, in terms of just keeping track of them, that's something we do very well. Well, we have one over here.
What happens when a satellite runs out of fuel?
So this is a good one. So what happens when the satellite runs out of fuel? So this is what we call end of life. We're coming up, and then this is, again, another thing on regulations is, well, what do you have to do when your satellite's done, when it's dead? And again, there isn't really a hard rule. We're getting close to having hard rules. I know Europe and ESA is leading the charge on this. For things that are in low Earth orbit, if you have enough fuel left at end of life, you can actively deorbit your satellite using your remaining fuel. So usually you keep a fuel in reserve in order to actively deorbit your satellite, but that only works if you're in a low enough orbit. If you're in too high of an orbit, there's no hope for that. You're up there forever. And this is one of the things I like to talk about. So I'll say, just to give you a ballpark here, something that's in a 200 to 250 kilometer orbit will be in space, will naturally deorbit because of drag, atmospheric drag, in a year or so. That's 250 kilometers. You go up to 500 kilometers, where Starlink is, you're talking about 20, 30, maybe 40, 50 years, depending on atmospheric conditions and space weather and whatnot. So something that's where Starlink is will will passively deorbit in 50 years at least. You go up to 1,000 kilometers, now you're talking 100 plus years. You go above 1,000 kilometers and that thing's basically up there forever. So this is something that we have to think about again in the long term when we're talking about space regulation is, well, what do we do when we have things that are up there forever? And I'll let you ponder that. Any last questions? One more from Joseph.
So, is it massive enough or dense enough that it'll bonk someone on the head when it comes down? When you say Starlink, for example, where there's 4,000 of them.
So this is something that NASA actually has a lot of guidelines on that people have followed. So one we've actually, they're again, not hard regulation, but lots of really good guidelines on what happens when you deorbit. So when you design a spacecraft, there is actually some consideration of, well, what will happen when this burns up in the atmosphere? And are any chunks going to be dense enough to make it through and cause possible harm or injury? I don't know exactly how well Starlink did on that data simulation. I'm assuming they were thought about that a lot because that's a real big concern for them because it's a liability thing. So I don't think that's something we have to be necessarily concerned about, but it does happen. You see it in the news every now and then, but usually that's because something was launched and didn't quite make it up high enough like they intended. Okay, I think we're done. Yes, thank you everyone.
Thank you again, Harry and Eden, for your amazing talks. Thank you all for coming out tonight. Our next show will be on June 20th at 7:30, again here. On your way out, tip your bartenders. We still have our merch out, and see you next month.
Woo!